Have you ever imagined a star so enormous that our sun would look like a glowing ember beside it? Somewhere in the darkness, far beyond our own warm little system, burns a giant whose energy could erase entire worlds in a single breath of light. Tonight, here in the quiet of the galaxy scientist, we'll drift toward this colossal sun and explore how something so massive forms, what holds it together, and what happens when its strength finally gives out. No rush, no worry, just gentle curiosity as you settle deeper into the night. When you're ready, we'll begin our journey toward the biggest star we've ever found. Among the countless stars scattered through space, one stands out like a quiet legend. Astronomers call it WHG 64, but many simply think of it as the Behemoth star. It is a red supergiant in the Large Magellanic Cloud, and its body is so swollen that, if you placed it where our sun is now, its outer layers would drift far beyond the path of Jupiter. It is not just large, it is so vast and so bright that it stretches the limits of what we thought a star could be, quietly rewriting the rules of how stars are born, live, and die. From Earth, we only see small points of light, yet each point is a roaring sphere of nuclear fire, where atoms are pressed together until they fuse and release energy. That energy pushes outward, holding the star up against its own gravity. These distant flecks bend time with their mass, warm worlds with their light, and paint entire galaxies with their glow. Some are gentle and steady, like our Sunday. Others are wild, with flames so bright they could swallow orbits and still keep burning. When astronomers call a star a giant, they are not just being dramatic, they are naming a stage in a star's life. For a long time, a star quietly burns hydrogen in its core, balanced between the inward pull of gravity and the outward push of fusion. Eventually, the hydrogen in the core thins out. The core shrinks and heats, and fusion shifts into a shell around it. The outer layers feel that extra pressure and begin to relax outward. The star swells, its surface cools and reddens, and it becomes a red giant, a puffed-up version of its former self. For stars that began much heavier than the sun, this swelling becomes extreme. Their cores burn hotter, their shells fiercer, and the outward push grows overwhelming. These stars can become red supergiants, and in rare cases hypergiants, swollen beings so large that an entire planetary system could fit inside their outer layers. To even picture them, we need new scales. Our sun has a radius of roughly 696,000 kilometers. A red supergiant like Betelgeuse can have a radius up to about 900 times larger than that of the sun, easily stretching beyond the orbit of Mars if placed at the center of our solar system. Even that is not the upper limit. WHG 64, the Behemoth star, is thought to have a radius up to about 1,540 times that of the Sunday place. It where our sun sits, and its glowing surface would lie past Jupiter's path. Its sheer size is hard to hold in the mind, yet size is only one way a star can be terrifying. There is also its luminosity, the total energy it pours into space every second. Our sun is a calm middleweight, bright enough to sustain life here on Earth. A giant like the Behemoth star shines hundreds of thousands of times more intensely, flooding its surroundings with light and heat. It burns fast, it burns bright, and it is destined to end its life in a spectacular, violent way. Being big is both a gift and a curse in the universe. A massive star lives in a kind of rush. In its core, gravity squeezes so fiercely that fusion races ahead, devouring fuel at a frantic pace. Where a star like the Sun may live for around 10 billion years, a truly gigantic star may last only a few million years. These are not slow, patient elders. They are young, furious giants living on borrowed time, destined to flare and fall long before the quieter stars have even reached middle age. Many of the largest known stars are not found in calm, orderly spiral arms, but in stranger places, irregular dwarf galaxies and starburst regions filled with chaos. The Large Magellanic Cloud is one of those places. It has lower metallicity, which, in astronomy, means that its gas contains fewer elements heavier than hydrogen and helium. That difference in chemistry changes everything. Heavy elements, the metals like carbon, oxygen, and iron, help hot gas lose heat. When gas cools, it tends to fragment, breaking into many smaller clumps that become many smaller stars. In a region where metals are scarce, that cooling is less efficient. Gas clouds stay warmer, resisting the urge to split into dozens of tiny pieces. Instead, they can collapse into only a few large seeds. Those seeds may become massive stars almost from the moment they ignite. Parts of the Large Magellanic Cloud behave exactly this way. Gas clouds there are poor in heavy elements, so they hold their warmth longer and collapse into fewer, bigger stars. The result is a breeding ground for massive star clusters, crowded neighborhoods where hundreds or thousands of stars are born, almost at once, in a burst of light. Inside these clusters, something like a quiet competition unfolds. Some stars form in the densest pockets or light up just a little earlier than the rest. They begin to pull in surrounding gas more efficiently, feeding on the shared reservoir. While many stars form with modest masses, a privileged few gather far more material, swelling rapidly. This is a kind of cosmic cannibalism, not of stars consuming stars, but of a few central giants monopolizing the food in the cloud, while their neighbors must make do with less. Those favored stars become the red supergiants and hypergiants, the massive monsters that dominate their regions. The behavior of the gas itself shapes their growth. Turbulent motions inside a cloud twist and fold it, creating knots of higher density where gravity can gain the upper hand. Rotation can funnel material inward, like water spiraling into a drain. When gravity finally wins over internal pressure and turbulence, a single forming star at the center can gather dozens or even hundreds of times the mass of the Sun before it settles into full, stable fusion. By the time its light reaches us, it is already a giant in every sense. There is a strange paradox hidden in all of this. The biggest stars are the hardest to make. They require rare conditions, special chemistry, and just the right flows of gas. Yet once they exist, they rule everything around them. Their radiation and powerful winds carve their surroundings, sculpting the clouds that once fed them. In some places, the pressure from their light and winds squeezes gas into new clumps, triggering fresh waves of star formation. In others, it blows the gas away, shutting down star birth for a while. These giants act as cosmic monarchs, deciding where new stars may arise and where space will stay empty and dark. Long ago, when the universe was young, such giants may have been more common. The first galaxies were filled almost entirely with hydrogen and helium. Heavy elements had not yet been forged in older stars, because those older stars did not exist. In that era, conditions likely favored the birth of what astronomers call population 3 stars, the very first generation. These stars may have been hundreds or even thousands of times heavier than the Sunday. We have never seen one directly. They are thought to have lived fast and died early, leaving behind only their chemical fingerprints. But stars like the behemoth in the large Magellanic Cloud might be distant echoes of that time, modern reminders of an ancient, chaotic way of making stars. To picture the home of WHG 64, imagine our Milky Way as a large, luminous city in the dark. Nearby, circling at a respectful distance of about 163,000 light-years, is a smaller, rougher town, the large Magellanic Cloud. It is a dwarf galaxy, irregular in shape and full of raw, unsettled energy. Though it has only about 1/10 the mass of the Milky Way, it produces a surprising number of very massive stars for the amount of gas it holds. Its star-forming regions, like the famous Tarantula Nebula, shimmer with clouds and clusters so active that they have become some of the brightest and most closely studied stellar nurseries in our cosmic neighborhood. The secret lies again in chemistry and chaos. The large Magellanic Cloud's gas has low metallicity, poorer in heavy elements than the gas of our galaxy. That means its clouds cool and fragment less, and more of the gas collapses into larger stellar seeds. This little galaxy does not favor balance. It favors extremes. It is the perfect cradle for outsized babies, like the behemoth star. Deep inside one dusty region of the large Magellanic Cloud, the behemoth star hides behind a thick veil of dust. Even with infrared instruments, it is difficult to see clearly. What we can tell, though, is striking. This red supergiant appears to have a diameter more than 1,500 times that of the Sun, and a light output hundreds of thousands of times greater, on the order of a few 100,000 solar luminosities. It is not just broad and bright, it is fragile. Its outer layers are barely held, drifting away in a slow, steady outflow, as if the star is exhaling itself into space. It is already in the process of letting go. Because the large Magellanic Cloud is relatively close, and because there is less intervening dust between it and us than in many directions within the Milky Way, it has become a natural laboratory for watching such giants. Telescopes, like the Hubble Space Telescope and the Very Large Telescope, can look into its clusters and nebulae with unusual clarity, catching massive stars at many different stages. Newborn blue giants, swelling red supergiants, and stars on the verge of collapse. By following them there, astronomers can test ideas about how stars evolve when they are pushed to the extremes of mass and luminosity. The dance between the Milky Way and the large Magellanic Cloud may be stirring these fires as well. The gravity of our larger galaxy pulls and tugs on the smaller one, squeezing some of its gas and stirring up new star formation. Some scientists think that, far in the future, the two galaxies may eventually collide, sending waves of new stars bursting into life, like sparks from a great cosmic flare. For now, the large Magellanic Cloud gives us a glimpse of conditions that resemble those in the early universe. Chaotic structure, low metal gas, and intense star-forming regions where giants are common. Watching a star like the behemoth in this setting does more than satisfy curiosity about a single strange object. It shows us how complexity and drama emerged from simple beginnings, how galaxies learned to build stars of every kind, from quiet suns to raging titans. The large Magellanic Cloud is more than just a small galaxy next door. Out in that rough little galaxy next door, where gas is thin on metals and thick with storms, it helps to imagine the whole place as a primordial forge. In that furnace, some stars grow merely enormous, and some step into something wilder. Red supergiants and hypergiants can look like the same kind of monster at first glance. Both are huge, both burn through their fuel in a rush, and both are headed toward disaster. But there is a quiet line between them, and the behemoth star drifts right along that edge. A red supergiant is already a star, past the calm middle of its life. It has left the main sequence, that long, steady phase, where hydrogen burns quietly in the core. Now heavier elements are being fused, and the outer layers have swollen outward and cooled. These stars usually carry between about 10 and 40 times the mass of the Sun, yet their radii can grow to hundreds, even more than 1,000 times the radius of the Sunday. Betelgeuse is the familiar example. A bloated, aging giant, glowing deep red in Orion's shoulder. It is huge, restless, and unstable, but it still lives within the broad expectations of stellar evolution. Hypergiants are a different kind of trouble. They are not defined only by being bigger, though many are. What marks a hypergiant is extreme instability and intense loss of mass. Yellow and red hypergiants occupy a narrow, dangerous window on the stellar life map. They burn fuel so violently and expand so far that their outer layers never truly settle. Gas and dust are constantly being driven off into space in heavy winds and eruptions. It is not just a swollen star, it is a star in a kind of continuous storm. The behemoth star fits this picture almost too well. Its radius is estimated to be more than 1,500 times that of the Sun, and it is wrapped in a vast shell of dust that extends almost a light year from its surface. That dusty envelope is made of its own discarded skin. It tells us that the star is losing mass at a furious rate, one of the key signatures of hypergiant behavior. Some astronomers still hesitate to label it a true hypergiant, and prefer to call it an extreme red supergiant. But its spectral lines, its winds, and its unsteady outer layers place it right on the brink of that rarer class. Part of why hypergiants are so uncommon is that the phase itself is brief. A massive star spends only a tiny slice of its life in such an extreme state, often for something like tens of thousands of years. In the story of a star that begins with millions of years of burning, this is just a flash. Only a few dozen hypergiants are known in our galaxy. They are snapshots of a breaking point, the moment when a star is tearing itself apart before the final act of collapse or explosion. Their light carries the fingerprints of this chaos. When astronomers spread their light into a rainbow, hypergiants show broad emission lines and odd distortions that hint at turbulence, shockwaves, and powerful winds flowing from the surface. They are not quiet giants glowing serenely in the dark. They are roaring furnaces under pressure, throwing off matter in messy bursts. Another way to see how close to the edge they live is to think about the Eddington limit, the balance point where the outward push of radiation equals the inward pull of gravity. Most red supergiants live safely below that line. Their brightness is high, but not so high that it rips the star apart. Hypergiants press right up against that boundary, and sometimes seem to push beyond it. When the light pushing outward becomes nearly as strong as gravity pulling inward, the star can no longer fully hold its atmosphere. The outer layers lift and drift away like mist from a too-hot pot. So red supergiants are immense and majestic. Hypergiants are short-lived and mythic in their instability, burning their candle at both ends and racing toward a final crescendo that will end as a spectacular supernova or a direct fall into a black hole. Within that wild company, the behemoth star stands out. If the universe kept a hall of fame for cosmic titans, this one would loom near the top. It is a swollen, burning presence in the large Magellanic Cloud, not even in our own galaxy, yet close enough for our telescopes to chase. It is so large, so luminous, and so deeply wrapped in its own debris that it forces astronomers to stretch their ideas about what a star is allowed to do. The star was first noted in the 1970s by Bengt Westerlund, Bengt Olander, and Hans Hedin, whose initials gave it the name WHG, followed by 64. Even early measurements marked it as extraordinary. Its radius appears to be around 1,500 times that of the Sunday. If you placed it where the Sun sits now, its swollen surface would envelop Mercury, Venus, Earth, and Mars, and reach close to the orbit of Jupiter. The numbers drift beyond comfort, so it helps to shrink them. Imagine the Sun as a tennis ball. On that scale, the behemoth star would be a sphere about the size of a football stadium, filling your whole field of view. It is not just broad, it is also intensely bright, shining with roughly a few 100,000 times the luminosity of the Sunday. Yet so much of that light is hidden from our direct view. The star is ensnared in a dense donut-shaped envelope of dust, made of its own expelled material. That thick veil absorbs and scatters its radiance, re-emitting much of it in infrared wavelengths rather than visible light. What looks like a faint, reddish smudge in a telescope is, in fact, a star pumping energy into a vast cloak of ash and gas. The envelope stretches to nearly a light year across, like a slow-moving shroud drifting outward, pushed along by the star's winds. It is a visible sign that the star is in the middle of self-destruction. For all that power, the behemoth star is relatively cool at its surface. Its temperature sits around 3,000 to 3,400 Kelvin, cool enough to be firmly classified as a red supergiant. Yet even among red supergiants, it sits in an awkward place. It lives near, and may even cross, the Hayashi limit, a theoretical boundary that says a star of a certain mass cannot remain stable at very low temperatures and very large radii. On the usual diagrams where astronomers plot stars by brightness and temperature, there is a region that should be forbidden. The behemoth star seems to hover near that forbidden edge, holding itself together where our equations suggest it should not. Some of its strangeness may come from companionship. It is still unclear whether the behemoth star is truly solitary. The heavy dust and the crowding of surrounding stars make it hard to be sure. Some models propose that a very hot, bright blue companion, perhaps an O or B-type star, might be orbiting nearby but hidden within the shared envelope. In that case, the system would be a binary, and interactions between the two stars, such as tidal effects or colliding winds, could help explain the extreme mass loss and the shape of the dust. For now, that companion remains hypothetical, a ghost partner inferred from hints rather than seen directly. Its home in the Large Magellanic Cloud is part of the story too. That galaxy's lower metallicity and vigorous star formation seem to encourage unusual giants. With fewer heavy elements in the gas, stars there follow slightly different evolutionary tracks. They can grow larger, shed mass in different patterns, and possibly die in more spectacular ways than similar stars in the Milky Way. The behemoth star appears to be a child of that environment, given permission to reach a size and instability we might not expect in our own more metal-rich galaxy. To feel its scale, it helps to slow down with the numbers. The Sun's diameter is about 696,000 kilometers. Multiply that by roughly 1,500, and you reach a diameter on the order of more than 1 billion kilometers. A star that wide, placed at the center of our solar system, would extend far beyond the orbit of Jupiter. Every rocky world and its moons would lie deep inside its glowing atmosphere. Even some of Jupiter's own moons could be submerged in the star's outer layers. The entire inner solar system would disappear into a red haze. Even that can feel abstract. So imagine a passenger jet flying along the Sun's equator at a normal cruising speed. It would need a little more than half a year, roughly 6 months, to make a full loop around the behemoth star. That same plane would spend something like 75 years, completing one slow circle. A human lifetime for one lap around a single star. Despite its enormous volume, the star is not proportionally massive. Estimates put its mass at a little more than 20 times that of the Sunday. That means its matter is stretched thin. The outer layers are like stellar fog, so diffuse that if you could fly a spaceship through them, you would feel less resistance than an airplane feels in Earth's air. This makes the star beautifully delicate and dangerously fragile. The larger and cooler it becomes, the closer it drifts to regimes where it must either contract or fling its own mass away. The Hayashi limit, that boundary between stability and collapse at low temperature, hovers over its existence like a quiet warning. The behemoth star also reshapes its surroundings simply by being there. Even with a cool surface, its huge area gives it a vast stage from which to radiate energy. The light and wind pouring off it heat nearby dust, push surrounding gas aside, and carve patterns through the cloud that once fed it. The region around it becomes a sculpted landscape of glowing grains and empty cavities, and the star's presence can either encourage new stars to form by compressing some pockets of gas or prevent star formation by sweeping material away. It is a kind of unintentional tyrant, shaping its neighborhood through heat and gravity alone. And still, it may not be the absolute largest. Other red hypergiant candidates, such as Stephenson 2-18, UY Scuti, and a few distant, dust-wrapped giants, might rival or surpass it in size, depending on how their distances and radii are measured. The behemoth star's own dusty veil makes precise measurements difficult. That uncertainty becomes part of its atmosphere. It is not only huge, it is elusive and strangely hard to pin down, pushing our ideas of what the word star can hold. To bring its power closer, imagine, just for a breath, that the behemoth star suddenly took the place of our Sunday. No long approach, no gradual brightening. One moment we orbit a modest yellow star, and the next, that star has been replaced by a red behemoth. There would be no morning. Earth and the nearby worlds would already be gone, swallowed deep inside the star's sprawling body. With a radius around 1 billion kilometers, roughly 1,500 times that of the Sun, the behemoth star's outer layers would engulf Mercury, Venus, Earth, and Mars, and stretch beyond the orbit of Jupiter. The inner solar system would be erased. The star's extended atmosphere would likely reach close to Saturn's path, turning the space where planets once moved into a hot, turbulent envelope of plasma. Even if some small planet somehow survived just outside this new surface, the conditions would be unbearable. The behemoth star emits on the order of hundreds of thousands of times more light than the Sunday. A world sitting near that border would be drenched in radiation. Surface temperatures would climb to many thousands of degrees Celsius. Any atmosphere would be stripped away, blown off into space. Oceans would be torn apart and flung away as superheated vapor and ions. High-energy light would bathe the surface in instant, lethal doses. The gravity of such a star would rewrite the layout of the system as well. With a mass perhaps 20 to 25 times that of the Sun, the behemoth star would tug more strongly on everything bound to it. The gentle ellipses of planetary orbits would warp. Some bodies might spiral inward and vanish into the star. Others could be slung outward, cast into deep space. The distant belt of icy objects beyond Neptune would be disturbed, and the remote cloud of comets far beyond that could be scattered like dust chaffed off a surface. On top of all this, the stellar wind would transform the quiet, near vacuum between planets into a stormy sea. Red supergiants like the behemoth star shed mass continually, and in this case, the outflow would be especially heavy. Streams of charged particles and dust would rush outward, turning space into a harsh environment where satellites and spacecraft could be ablated, eroded, or melted. Any thought of gentle space travel would fall away in the face of such weather. The region where conditions might be soft enough for liquid water, the habitable zone, would be pushed far outward to the very edges of what we now think of as the solar system, perhaps even beyond that faint border, as if the only place left for calm were almost beyond the behemoth star's reach. Out near the pale orbits of Uranus and Neptune, where our old sun once seemed faint and gentle, everything would twist into something harsh. Worlds that were once cold and quiet could become blazing furnaces. Icy moons would not stay frozen marbles of rock and water. Their surfaces would boil, crack, and burst as the behemoth star's swollen atmosphere and fierce light reached them. And even then, even after turning so much of the system into vapor and fire, this star would not find peace. Stars this huge live quickly and burn through their lives in a rush. In cosmic terms, the behemoth star is already living on borrowed time, drifting toward a fate where it must either collapse, explode, or peel itself apart in some spectacular final act. Its arrival would not just end the solar system we know, it would lay down the dust and debris for an entirely new, strange arrangement of worlds, built around the fading echo of a star that was always too big to last. Part of what makes this star so overwhelming is not only its size, but its light. The behemoth star is thought to radiate roughly 280,000 times more energy than the Sunday. Our gentle sun already does an astonishing job, quietly sending out enough warmth and light to keep Earth's climate, oceans, and air moving from about 150 million kilometers away. Multiply that gift of energy by hundreds of thousands, and you begin to sense what the behemoth is doing each second. It is not just the difference between a candle and a campfire. It is more like comparing a glowing match to the explosion of a small world. All of that luminosity has consequences. Light, when it is intense enough, does not simply illuminate. It pushes. The pressure of the behemoth star's radiation alone is strong enough to drive its own material off its surface, blowing out powerful stellar winds and building enormous shells of dust. Most of its energy leaks out in visible and infrared light. And if there were no veil around it, a star like this could be spotted from far across intergalactic space. But the behemoth has wrapped itself in its own storms. A thick cloud of dust hides much of its true brightness, turning a blazing monster into something that looks modest from far away. To see past that veil, astronomers turn to infrared telescopes on the ground and in orbit, instruments on the Very Large Telescope in Chile, and observatories like the Spitzer Space Telescope collect the longer wavelengths that slip through the dust more easily. By spreading that light into a spectrum, they can read the star's fingerprints, how much energy it releases, which elements float in its atmosphere, and how quickly it is throwing its outer layers away. The picture that emerges from those observations is clear, in one way at least. This blinding light comes from a star that is in trouble. Our sun is still only in middle age, with roughly 5 billion years of calm nuclear burning ahead of it. The behemoth star, by contrast, will live out its life on a timescale of only a few million years, and most of that may already be behind it. A star that bright must burn fuel at a rate that cannot be sustained for long. It is like a nuclear engine pushed to maximum power, knowing that every moment of brilliance is also a step closer to exhaustion. that same luminosity turns the surrounding space into a harsh, scouring environment. The intense light tears molecules apart, breaks delicate chemical bonds, and bathes everything nearby in radiation strong enough to strip atmospheres and shatter the building blocks of life. Any unlucky planet in a close orbit would be hammered by high-energy photons. Its air would be peeled away, its surface scorched, its water ripped into steam and then into charged particles. The behemoth star is not a gentle host. It is a furnace that fills its surroundings with light, heat, and quiet ruin. And yet, inside that violence there is subtlety. Stars like this often show small changes in brightness, waves of brightening and dimming over time. These variations can come from convective instability, from great cells of hot gas rising and falling inside the star, and from changes in its outer layers as they swell and contract. Each flicker can be a hint that something inside has shifted, that deep in the core, new elements are being fused, or that the star is moving one step closer to its final collapse or explosion. Why, then, do we devote so much attention to something that seems so destructive? In part, because stars, like the behemoth, are rare, and they hold clues to how the most massive stars in the universe live and die. Their brightness makes them visible across large stretches of space, letting us study stages of stellar evolution that would otherwise be hidden. Watching such a star is like watching the end of many other stars in slow motion. Its story helps scientists understand how galaxies change, how heavy elements are forged and scattered, and how light and matter interact at their extremes. Wrapped around this star is one of the most striking features of all, a vast cloak of dust, about a light year across. This dusty shell did not appear all at once. It is the accumulated result of countless outbursts and winds as the star, in its late burning phases, hurled gas, plasma, and freshly forged elements into space. As that material moved outward, it cooled and condensed into tiny grains, made of silicates, carbon compounds, and other hardy substances that do not melt easily. Over time, these grains built up into a thick circumstellar jacket, a layered shell around the star. Observations from the Very Large Telescope in the mid-2000s revealed that this shell is not a simple, smooth sphere. Instead, the dust seems to be gathered into a torus, a donut-shaped ring. This suggests that the star's rotation, winds, and possibly magnetic fields are funneling material into particular directions rather than letting it escape evenly. It is as if the behemoth star is wearing a cloak tailored by its own spin and instability, with denser folds in some directions and thinner veils in others. This torus does more than hide the star. It transforms the light. A great deal of the energy pouring out from the behemoth star is absorbed by the dust grains and then re-emitted at longer infrared wavelengths. That is why infrared telescopes are so important for studying it. In ordinary visible light, the star is muted, partly erased by its own breath. In the infrared, the cloak itself glows, outlining the structure of the dust and the scale of the material that has been lost. The weight of that cloak is staggering. Astronomers estimate that it contains between roughly 3 and 9 times the mass of the Sun, all of it material that once belonged to the star and has been thrown away. That means the behemoth star has already shed more mass than many whole stars ever possess. Each second, more of its substance leaks out into the void. It is a sign not of calm middle age, but of old age and decay, a hint that the star is nearing an end it can no longer avoid. For the space around it, a dust shell of that scale is a kind of catastrophe. The radiation from the star pushes the dust outward, driving a shock front that sweeps through the surrounding region. Any planet that once orbited nearby would now be buried under layers of irradiated debris and broken molecules. There is no comfortable distance from such a star, only degrees of damage. Closer in, rock and ice are vaporized. Farther out, fragile surfaces are scarred and sterilized. As dramatic as the present is, the most astonishing moment is still to come. When the behemoth star finally exhausts the fuel in its core and collapses, it will almost certainly go supernova. The resulting shockwave and burst of light will slam into the dust shell, heating and illuminating it from within. For a time, that torus may blaze as a bright nebula, visible across great distances, a glowing echo of the star's last breath. The dust that now hides the star will become the canvas for its final flare. Part of the behemoth star's mystery lies in the fact that, by some measures, it should not be able to stand as it does. In the study of stars, there is a guideline called the Hayashi limit. It describes a boundary where cool stars of a given mass cannot become larger and cooler without losing their delicate balance between gravity pulling inward and pressure pushing outward. On the Hertzsprung-Russell diagram, where stars are arranged by brightness and temperature, the Hayashi limit marks a kind of wall for fully convective cool stars. Go too far past that wall, and hydrostatic equilibrium breaks down. The star must contract or shed mass to regain stability. For high-mass red supergiants, the idea is similar. There should be a maximum size and minimum temperature they can maintain without falling apart or throwing off matter uncontrollably. Yet the behemoth star appears to have a diameter around 1,500 times that of the Sun, with a surface temperature low enough to place it very near, and perhaps beyond, where that limit would normally sit. In other words, by the simplest rules, it should not be as large and cool as it is for as long as it has been. The way it manages to exist at all may lie in its very fragility. Because the behemoth star is so swollen and its surface gravity so weak, it is losing mass at an extraordinary rate. That steady shedding of material cools the outer layers and alters the internal pressure, allowing the star to hover for a while in a state that would otherwise be unstable. The dust envelope does not just hide the star. It is one of the reasons the star has been able to reach this strange state. It is, in a sense, keeping itself balanced by constantly throwing parts of itself away. Other factors may also be helping it cheat the usual rules: rotation that redistributes energy, magnetic fields that channel flows of gas, or even the gravitational pull of a still unconfirmed companion star. These influences could stir the interior, alter convection, and stretch the boundaries of what is possible for a red supergiant. Watching the behemoth star is like watching a skyscraper swaying in a strong wind, its frame creaking, its outer walls shedding pieces, and yet somehow still standing. In that way, the behemoth star acts as a challenge to our models, a kind of cosmic rebel. It is so massive, so bright, and so unstable that it seems to mock the neat diagrams we draw to explain stellar life cycles. But that is exactly why it is valuable. When you find an object that does not fit the rules, you do not ignore it. You lean in, you measure, you think again, because understanding why it does not fit may show you which of the rules need to be rewritten. Underneath all of this is the simple, dramatic fact that the behemoth star is falling apart. Every star loses material over time, but the scale here is extreme. Our Sun, for instance, sheds a steady wind that carries away millions of tons of matter each second. That sounds immense until you compare it to the behemoth star, which may be losing mass at a rate many thousands of times greater, perhaps a tiny fraction of a solar mass each year. In practical terms, That is like ejecting the mass of Earth again and again on human timescales. That lost material becomes the dust envelope we see, a vast, opaque cocoon stretching up to a light year across. It is made from the star's own gases and elements, cooled and assembled into complex molecules and solid grains. It hides much of the behemoth star's visible light, leaving us with a ghostly, dimmed view despite its true power. In another sense, it is the record of the star's slow disintegration, layer after layer, gently drifting away. The balance that holds a star together is delicate. When so much mass is removed from the outer regions, the pressures inside shift. Gravity grips the core more tightly, while the star's swollen atmosphere becomes easier to disturb. In the behemoth star, low surface gravity, strong pulsations, radiation pressure, and perhaps magnetic fields all combine to shake the outer layers loose. Mass loss likely comes in waves, with quieter periods followed by outbursts, like a restless volcano that seems calm until it suddenly hurls ash into the sky. With each episode, the core becomes a little more exposed. Bit by bit, the behemoth star is stripping itself down toward the moment when its inner engine can no longer support the weight above it. Then gravity will win outright, and the star will collapse in on itself in a final, violent transformation. The very act of falling apart becomes the path toward its end. And yet, there is a strange, gentle beauty in this decay. The material that leaves the star is not empty. It carries carbon, oxygen, nitrogen, and heavier elements forged deep within the core. Those elements drift outward, mixing with the surrounding gas, seeding the region with the ingredients that future stars, planets, and perhaps even living beings will need. In dying, the behemoth star is quietly enriching the universe around it, scattering the raw materials for life into the dark. Across the galaxy, the story of life is written in the deaths of stars like this one. When giants, such as the behemoth star, finally give up their last breath, they do not disappear quietly. They leave behind the raw ingredients of future worlds, the metals that will cool into rock, the oxygen that will dissolve into seas, the carbon that might one day sit inside a nervous system capable of feeling joy and pain. For the behemoth star, though, this ending is not a single moment. It is a long, slow fall. Every pulse of mass that it throws into space is another tick on a cosmic clock. Every wave of dust drifting outward is a soft whisper that the end is drawing near. And when that end comes, it will not be gentle. The final act of a star this large could be one of the most terrifying, beautiful displays the universe offers. A flash so powerful that any nearby civilization would witness night turned into day. To understand what is happening behind that dusty veil, astronomers turn to a kind of quiet language, stellar spectroscopy. Instead of peeling back layers with hands, they use instruments that split starlight into rainbows, reading the thin, dark lines and bright bands that appear there, the way you might read letters on a page. At first glance, the behemoth star's spectrum looks chaotic. The light we receive is reddened and dimmed, chewed up by the dense cloak of dust around it. In ordinary, visible light, the star is almost hidden, so observers shift their gaze to infrared and radio waves, the longer wavelengths that slip more easily through the haze. There, the curtain begins to lift. With huge telescopes, such as those at the European Southern Observatory, scientists divide the behemoth star's light into its component colors. In that spread-out light, thin marks appear, spectral lines. Each line is a signature of a particular atom or molecule. They act like tiny identification cards, telling us who is present in the star's atmosphere and its surrounding shell. In the behemoth's case, they have found silicon monoxide, carbon monoxide, and water vapor, along with hints of more complex molecules forming in the dust. What is astonishing is not only that these substances exist there, but that they survive under such intense radiation and in such a wildly disturbed environment. The dust cloud itself is not just drifting in silence. It is being warmed by the star's enormous luminosity and radiates energy of its own, especially in the infrared. Seen in those wavelengths, the envelope glows with a soft, eerie light. Careful mapping suggests that the dust is not simply arranged in a neat sphere around the star. Instead, it appears to be gathered into a torus, a donut-shaped ring, perhaps sculpted by rotating jets of outflow or the pull of an unseen companion. In that bright ring, temperatures can range from a few hundred to over 1,000 degrees Kelvin. Those temperatures are cool compared to the star's surface, but still warm enough for grains to grow, collide, and change. Long before any rocky planet or icy world ever assembles, the building blocks are already there, drifting in this luminous fog. Spectroscopy does more than list ingredients. It also measures motion. Some spectral lines from the behemoth star are shifted slightly toward longer, redder wavelengths, a sign that some gas is moving away from us. Other lines are shifted toward shorter, bluer wavelengths, showing material ejected in our direction. The pattern is not symmetric. It hints that the star is not shedding its mass evenly, but in lopsided bursts, guided by rotation, magnetic fields, or perhaps the gravity of something nearby. There are even emission lines in the spectrum that do not quite fit what we expect from a red supergiant. They point to shock waves and high-energy reactions in the region around the star, as if the whole envelope were continually being rattled from within, each invisible tremor setting off brief and exotic chemical dances. And still, after all of that, we do not truly see the star itself. The photosphere, the visible surface of the star, is buried under layers of gas and dust. What reaches us is a softened glow, light that has been absorbed, scattered, and recolored on its way out. We look, in a sense, not at the star, but at the illuminated smoke around it. Within that smoke, there may be another actor. Massive stars rarely live entirely alone. Many of them are born in pairs or small groups, held together by gravity and circling each other over millions of years. Because of this, astronomers have long wondered whether the behemoth star has a companion hidden somewhere inside its thick dust. If it does, that partner could change everything about how the star loses mass, how it will explode, and what it will leave behind. Searching for such a companion is difficult. The very dust that makes the behemoth star so interesting also hides much of the evidence. Visible light is blocked and smeared out, so observers turn again to infrared imaging, radio interferometry, and careful measurements of how the star's spectral lines shift over time. One promising clue would be a tiny, repeating wobble in the star's motion, the subtle tug of a partner's gravity. So far, no such simple pattern has been confirmed. What has been seen are asymmetries in the dust shell, lopsided structures, arcs, and clumps that suggest something more complicated than a single star, quietly puffing in all directions. The torus of dust around the behemoth star, in particular, resembles the outflows that often appear in binary systems, where one star's winds are carved and redirected by another's presence. Observations with the Very Large Telescope Interferometer have hinted at disturbances and knots in the envelope that could be signs of a nearby object moving unseen within the fog. Some models go further and suggest that if a companion exists, it might be a hot, massive O-type star still on the main sequence. small compared to the behemoth in size, but still powerful in its own right. Such a star could be orbiting inside the dust cloud, feeding on the gas and dust blown off by the red supergiant, like a parasitic twin. In that case, the system would be a mass transfer binary, with streams of material flowing from the swollen giant toward the smaller, denser companion. Around that companion, an accretion disk might form, potentially glowing in X-rays. But the dust shell is so thick that any such X-rays could be absorbed before escaping, leaving us only indirect hints, polarization measurements, studies of how the star's light becomes lined up in particular directions as it scatters off dust, also suggests that the envelope is not perfectly spherical. Light seems to be shaped by structures and flows that do not match a simple, single-star wind. Still, no clear image of a companion has been captured. No long, steady pattern in the star's radial velocity has been firmly tied to another star's orbit. At the moment, the question may not be whether the behemoth star could have a partner, but whether we can ever see that partner through the veil in time. If a companion is there, it will likely change the ending. A partner could draw material away more efficiently, speeding up the behemoth star's mass loss. It might help shape the final explosion, turning it into a lopsided supernova that sprays matter more strongly in one direction than another. Some of the most powerful stellar blasts we know involve close, massive binaries, where two large stars interact or merge. The behemoth star may be standing at the threshold of such a fate, or it may be alone. Either way, the story ends in collapse. At the heart of that story lies a simple balance. Every star, no matter how large, lives between two great forces: gravity pulling inward and pressure pushing outward. Gravity wants to draw all the gas toward the center, compressing it into the smallest possible sphere. Pressure, born from nuclear fusion in the core, pushes back. For most of a star's life, these two influences reach an uneasy truce. The star's size and brightness adjust until the inward pull and outward push match. The behemoth star has driven itself to the edge of this balance. Its radius, more than 1,500 times that of the Sun, stretches its outer layers to such low densities that they resemble a thin fog rather than a solid surface. Gravity at the surface is weak. Gas can drift lightly there, easily stirred and easily lost. The star is no longer a neat, round ball. It is more like a trembling cloud, its outer layers pulsing and leaking into space. The Hayashi limit hangs over this configuration. That theoretical boundary marks the largest radius and lowest temperature a fully convective star of a given mass can have, while still holding hydrostatic equilibrium. The behemoth star seems to sit at, or even beyond, that limit. That suggests that the interior is unstable, already experiencing deep convection and core instabilities that make large-scale mass ejections more likely. Inside, the fusion story has marched far beyond simple hydrogen burning. Helium in the core has been fused into carbon and oxygen. In deeper, hotter layers, heavier elements such as neon, magnesium, and silicon begin to appear. Each new stage of fusion consumes its fuel more quickly. In a star this massive, silicon, burning the last step before iron dominates the core, may last only days. The same mass that once helped the star shine so brightly now drives it toward collapse. The gravitational pressure at the center becomes overwhelming. The core enters a degenerate state, where the pressure is controlled not by temperature, but by the quantum arrangement of the particles themselves. In this regime, the usual rules of heating and expansion start to fail. There is a limit, known as the Chandrasekhar limit, at about 1.4 times the mass of the Sun, beyond which even this quantum pressure cannot support the core. If the behemoth star's core crosses that threshold, gravity will finally win without restraint. As it does, the core collapses inward at a significant fraction of the speed of light, compressing matter into an object smaller than a city and denser than anything we can comfortably imagine. In a matter of seconds, the collapse halts as the core becomes a neutron-rich ball, where a teaspoon of material would weigh billions of tons. The infalling outer layers slam into this suddenly rigid core and rebound, sending a powerful shockwave racing outward. At the same time, an enormous flood of neutrinos, elusive particles born in the heart of the collapse, stream through the star. A fraction of their energy couples to the outer layers, helping to drive the shock further. The result is a core collapse supernova, a blast so energetic that for a short time, it can outshine an entire galaxy. For weeks, the dying behemoth star could appear as bright as a small sun to any world, with a clear view, turning night into ghostly day. If such an event occurred within our own galaxy, earthly observers would see a new star suddenly flare in the sky, brighter than the moon, casting sharp shadows at midnight, and perhaps even visible in daylight as a second, pale sun. Telescopes would lock onto it, recording every change in brightness, every shift in spectrum, every widening of the expanding debris. What remains after the light fades depends on how much mass the star has managed to lose before this final act. If strong winds and violent outbursts have stripped away enough of the outer layers, the core left behind might be small enough to settle as a neutron star. In that case, a city-sized object made almost entirely of neutrons would spin in the dark, held up by neutron degeneracy pressure, its crust perhaps wrapped in intense magnetic fields. If too much mass remains, even that exotic pressure will not be enough. The core will continue to collapse into a black hole, a region of space where gravity becomes so strong that not even light can escape. A silent scar in space-time that quietly consumes anything that drifts too close. Either way, the behemoth star's story ends in transformation. The dust, the winds, the shockwaves, and the final collapse will all contribute to the galaxy's ongoing life. From its slow unraveling and sudden death, new clouds will form, new stars will be born, and somewhere, someday, another being may look up at its sky and wonder where the elements in its own body once came from, never knowing they were forged in the heart of a star too large to last. When a giant like this finally tears itself apart, the story does not end with the flash. The supernova's ashes drift outward, mixing into the thin gas between the stars, carrying heavy elements like gold, uranium, and platinum. Over millions of years, those atoms will be folded into new clouds, new planets, new oceans, and into the fragile bones and nervous systems of creatures that can one day feel wonder and fear. Everything around you, from your body to the object resting in your hand, was once part of a star that died. These enormous deaths are not only endings, they are the quiet beginnings of everything that follows. For the behemoth star, the question is simple and severe. What will it leave behind? When a massive star collapses, its core can take one of two broad paths. If, after all the shedding and blasting, the remaining core is a bit less than about 2.5 times the mass of the Sun, it can settle as a neutron star, held up by the quantum pressure of tightly packed neutrons. But if the core is heavier than that, gravity does not stop. It overwhelms even that exotic pressure, and the core continues to shrink until it forms what our equations describe as a singularity. a region from which nothing, not even light, can escape. That is how a black hole is born. The behemoth star seems destined for this darker route. Its total mass is thought to have started at several tens of solar masses, perhaps between about 25 and 40 times the mass of the Sunday. Strong winds and violent eruptions have peeled away much of its outer layers, building the dusty cloak that now hides it, and we cannot weigh it precisely. But its core is almost certainly still too heavy to end as a simple neutron star, even if it has lost a large fraction of its original bulk. In that sense, it is not just a candidate for black hole birth. It is walking toward an almost unavoidable fate. For stars this massive, a black hole is not a strange accident, but the natural conclusion of their lives. Once the supernova's brief brightness has faded, gravity will quietly finish its work. Space and time near the core will fold inward. Matter will cross a boundary from which it cannot return. Information, according to some views of physics, may be scrambled in ways we do not yet fully grasp, though ideas like Hawking radiation hint that nothing is ever completely lost. The newborn black hole may contain only a handful of solar masses, perhaps 5, perhaps 10, or a little more, packed into a radius of only a few tens of kilometers. Smaller than a city, heavier than many stars, and so intense in its pull that it can bend light, slow clocks, and distort the paths of anything that strays too close. If the behemoth star truly has a companion, the story might grow even more dramatic. The black hole could begin to draw matter from the surviving star, forming a hot, bright disk of infalling gas around it. That disk would shine in X-rays, and thin, focused jets of material could be launched at nearly the speed of light, piercing the surrounding space. But it is just as likely that the black hole will spend most of its existence drifting quietly, sipping at the thin gas between the stars, merging slowly with its environment. In the far future, it could join other black holes near a galactic center or collide with another of its kind, shaking the fabric of space-time with gravitational waves. The behemoth star is not the only giant that has stretched our sense of size. Before its shadowy bulk in the large Magellanic Cloud captured so much attention, there was Scuti, a red supergiant that once held the informal title of largest known star by radius. If the behemoth is the hidden colossus wrapped in dust, then Scuti is the more flamboyant monarch inside our own Milky Way, glowing a deep ruby in the constellation Scutum. It lies roughly on the order of 10,000 light-years from us, and estimates of its radius suggest it extends well over 1,000 times the Sun's size. Place it at the center of our solar system, and its surface would stretch beyond the orbit of Jupiter, swallowing the inner planets and bathing the outer ones in red light. Scuti is also extraordinarily luminous, shining hundreds of thousands of times more brightly than the Sunday, yet its mass is surprisingly modest for such a vast star, likely only several to perhaps around 10 solar masses. The reason is its low density. Like many red supergiants, it is more like a huge, warm bubble than a tightly packed sphere. Its outer layers are so thin and extended that standing on its surface would feel more like drifting in a diffuse sea of plasma than standing on anything solid. It flickers and pulsates, shedding mass in winds that will eventually set the stage for its own supernova. Its story has also reminded astronomers how difficult it is to measure such stars precisely. Pulsations, dust, and hazy edges all conspire to shift its estimated size over time. Even so, Scuti has earned its place as one of the great examples of how big a star can appear while remaining only modestly heavy. Before Scuti, another name loomed large, VY Canis Majoris. For a time, it was hailed as perhaps the largest star we knew, a red supergiant in the constellation Canis Major, several thousand light-years away. At its most expanded, it may reach more than 1,000 times the Sun's radius, wide enough that, if it sat where our Sun does, its surface would extend far beyond Jupiter's path. Its mass, however, is only on the order of a couple of dozen solar masses, not extraordinary in itself. What makes VY Canis Majoris so striking is how violently it is coming apart. It is a high mass-loss star, casting off its outer layers in powerful winds that have created a sprawling nebula of gas and dust around it. Looking at VY Canis Majoris is like trying to see a lighthouse through a storm. The dust clouds swirling around it cause its light to flicker and dim, not because the star is always changing inside, but because our view is constantly being rearranged. This has made its true size and structure hard to pin down, and newer measurements have revised its radius downward from earlier, more dramatic claims. Even so, it remains a crucial laboratory for understanding how unstable red supergiants behave near the end. When it finally explodes, it is likely to do so as a spectacular supernova, or even a hypernova, possibly bright enough to rival the full moon in our sky for weeks. Its last act will not be quiet. Then there is Stephenson 2-18, perhaps the only star that might truly rival or exceed the behemoth in sheer bulk. Discovered in the 1970s and nestled in a rich cluster known as Stephenson 2, it lies roughly on the order of tens of thousands of light-years away in the direction of Scutum. It is one of the most luminous red supergiants ever observed, with a light output at least several 100,000 times that of the Sun, and possibly more depending on how much dust and distance we assume. Like its cousins, it is enormously swollen, with gravity barely holding its outer layers in place. Its mass is thought to be on the order of several tens of solar masses heavy, but not as wild as its volume might suggest. Once again, the universe shows that size and weight do not always move together. Because Stephenson 2-18 is so distant and so wrapped in interstellar dust, much of what we know about it comes from indirect clues: its brightness, its color, and models of how stars evolve. Even with these uncertainties, it stands out as a strong contender for the largest star we have measured so far. It is also old by the standards of massive stars, already in the late stages of its life, and will likely end as an especially energetic supernova or hypernova, perhaps leaving a black hole behind. Whether or not it holds the absolute record for size at any given moment, it marks one of the outer edges of what stellar evolution can do. Closer to home, in the constellation Cepheus, another red giant has earned a more poetic title. Mu Cephei, sometimes called the Garnet Star, is one of the deepest red stars visible to the naked eye. William Herschel once described its color as deep garnet, and the name stayed. This star is also impressively large, with a diameter thought to be well over 1,000 times that of the Sun, making it one of the biggest known stars in our galaxy. If a world orbited at the edge of its photosphere, that orbit would lie roughly where Jupiter or Saturn circle in our own system. Billions of Earth-sized planets could fit inside its volume. Mu Cephei is thousands of light-years away, and astronomers still debate its exact distance, which makes its true size a little uncertain. Even so, its immense luminosity, hundreds of thousands of times greater than the Sun's, and its relatively cool surface temperature around a few thousand degrees Kelvin show that it, too, is in its final chapters. Like the behemoth star, it has lost a great deal of mass already, casting its upper layers into space in a strong stellar wind. Those outflows carry carbon, oxygen, and heavier elements into the surrounding interstellar medium, quietly enriching the galaxy with the ingredients needed for future stars and planets. In the end, all of these giants, from the behemoth star cloaked in the large Magellanic Cloud, to UY Scuti, VY Canis Majoris, Stevenson 2-18, and Mu Cephei, will leave the same kind of legacy. Their supernova remains will drift outward, seeding the darkness with heavy elements: gold in rings, calcium in bones, iron in blood, silicon in glass, uranium in the heart of reactors yet to be imagined. These immense deaths are not just catastrophic finales. They are how galaxies grow rich. They are how the universe learns to build worlds. And on some of those worlds, beings who can step outside at night, look up at the stars, and feel, without quite knowing why, that they are made of something ancient and brilliant that once burned far away. Mu Cephei, the deep garnet star, will almost certainly one day end in a supernova of its own, leaving behind either a compact neutron star or a dark black hole. For now, though, it still hangs in our sky like a distant ember, a reminder that these monsters do not only live in faraway galaxies. Some of them burn quietly within our own. Not all giants are cool and red. Some choose a different path, trading size for intensity. These are the blue supergiants, stars that burn so fiercely they barely have time to age. Where red supergiants like the Behemoth Star and Mu Cephei loom vast and relatively cool, blue supergiants blaze with searing heat, living fast and dying in a rush. They are among the hottest and brightest stars in the universe, so luminous that, from the right angle and distance, a single one can rival the glow of a small galaxy. Rigel in Orion is a familiar example, a bright blue-white lantern in the winter sky. It shines roughly 120,000 times more brightly than the sun, with a surface temperature of around 12,000 Kelvin. Yet despite its grandeur, Rigel's life is brief. A few million years from birth to death is all a star like this gets, a heartbeat compared to the sun's billions of years. These stars begin their lives with masses perhaps 20 to 50 times the sun's, sometimes more. That weight crushes their cores so fiercely that nuclear fusion races ahead, turning hydrogen into helium, then forging heavier elements at a breakneck pace. Radiation from those reactions tries to blow the star apart. Gravity drags everything inward. For a while, a fragile truce holds. When the fuel begins to run low, the balance tips violently. Where many massive stars swell and cool into red supergiants before they die, some blue supergiants end almost straight from their hot, bright state. They can explode as Type II supernovae, tearing themselves apart. The most extreme may launch narrow beams of gamma rays that flash across whole galaxies. If such a beam ever pointed directly at a nearby world, it could scrub its surface clean of life in moments. Fortunately, there are no known blue supergiants close enough to Earth and pointed in just the wrong way to pose that kind of danger. Still, their deaths matter deeply. The debris of their explosions is rich in iron, calcium, gold, and other heavy elements that later become part of planets and people. In their short lives, they are like cosmic alchemists, turning the simplest elements into the complex ingredients of everything solid and living. Some of these blue giants may not even grant us the spectacle of a visible supernova. There are signs that a few might collapse directly into black holes, skipping the bright flash altogether, simply winking out and leaving only their gravity behind. That quiet vanishing is part of what makes them so haunting. There is another, rarer group of stars that almost seem to fall between categories: the yellow hypergiants. If red supergiants are vast titans, and blue supergiants are white-hot furnaces, yellow hypergiants are storms made of starlight. They are among the most unstable and least understood stars we know, changing quickly and shedding mass in violent bursts. Only a handful have been identified in our entire galaxy, and their rarity makes them feel like myth. Yellow hypergiants seem to represent a short, chaotic phase in the evolution of very massive stars, often somewhere between the red supergiant and blue supergiant stages. Their surfaces glow at temperatures of roughly 4,000 to 8,000 Kelvin, putting them in spectral classes similar to that of our Sun, but their luminosities are hundreds of thousands of times greater. They shine so intensely that their outer layers are barely bound. Strong winds and sudden outbursts continually strip them, as if the stars are trying to tear themselves apart. Rho Cassiopeiae is one of the best studied examples. It sits a few thousand light years away and radiates roughly 500,000 times the light of the Sunday. Astronomers have watched it undergo massive eruptions, in which it throws out several Earth masses worth of material in just a few months. After such an event, the star can dim noticeably as newly formed dust clouds briefly smother its light. Another remarkable yellow hypergiant, HR 5171, is so bloated that if placed at the center of our solar system, its surface would stretch beyond Jupiter's orbit. It is part of a binary system, and there are signs that matter flows from one star to the other, perhaps spiraling them toward a future merger. Some models suggest that such a collision could create an exotic hybrid object, where a compact core, like a neutron star, sinks into the envelope of a giant, blurring the line between two very different kinds of stars. We see so few yellow hypergiants because this phase is extremely short, lasting perhaps only tens of thousands of years. For stars that already live fast and die young, that is just a flicker. But by watching these unstable giants, astronomers learn how stars lose mass, how their surrounding shells of gas and dust form, and how the early stages of a supernova can already look messy and asymmetrical. The rings of gas and dust that yellow hypergiants throw into space will one day become part of new clouds, new stars, and new planets. All of this invites a quieter question. Could planets ever circle a monster like the behemoth star and survive even for a while? If we placed that star at the center of our own system, its swollen surface would stretch beyond the orbit of Jupiter. Any planet that once traced a path where Mercury, Venus, Earth, or Mars now move would be swallowed or torn apart by the star's extended atmosphere. Even far from the surface, its light and wind would be overwhelming. Life as we know it would not simply struggle, it would almost certainly fail. In principle, planets could form around a massive star in its earlier, calmer stages. But as the star grows into a red supergiant or hypergiant, its heavy winds and shifting mass would make its gravitational grip on nearby objects unreliable. The behemoth star is already losing matter at an extraordinary rate, flinging gas and dust outward in flows that dwarf anything our Sun produces. Those winds would drag on any close-in planets, pulling them into decaying orbits or kicking them outward into interstellar space. Even if a planetary system once existed, it might already have been largely erased by the star's current phase. Because the star is so large and its surface gravity so low, there is also a strange region around it where orbits would be especially unstable. Too close, and dust, rocks, or rogue planets could spiral inward and be consumed. Too far, and the same winds that strip the star might nudge objects away, Only at great distances, far beyond where Neptune orbits in our own system, might there be a chance for long-lived paths. From such a world, the behemoth star would be a vast red presence in the sky, dominating the horizon, its light filtered through veils of moving dust. True darkness might never fall, only deeper shades of crimson twilight. Even there, the environment would be harsh. The planet's surface would likely be cold because of the distance, but the radiation washing over it could still be intense, especially if the star flared or changed. Any life would almost certainly need protection, perhaps deep underground, beneath thick ice, or in buried oceans warmed by internal heat. Instead of drawing energy from gentle sunlight, organisms might rely on chemical reactions driven by minerals and geothermal warmth, the way some microbes on Earth live around deep-sea vents. Others might evolve pigments that absorb and reshape high-energy radiation, turning what would be deadly for us into a usable source of power, like living solar panels built for a sky that never softens. The orbits of such planets might not be tidy circles. The gravity field of a giant, unstable star can be complex, especially if it has a companion. Worlds could follow long, stretched paths, spending part of their year closer to the star in blistering conditions, and part of it in distant, frozen stretches. Life, if it appeared at all, would have to endure wild swings in environment, perhaps hibernating for long periods, changing shape over time, or clinging to the few regions that stay relatively moderate. Over all of this hangs a more fundamental limit: time. Our sun measures its life in billions of years. A star like the behemoth measures its in only millions. From the moment any hypothetical world cools enough for chemistry to become interesting, the clock is already running fast. Eventually, inevitably, the behemoth star will reach the end of its fuel and collapse. The resulting supernova will send out a wave of energy so powerful that anything within dozens of light years will be bathed in radiation and shock. For any fragile biosphere in that neighborhood, the star's long, warm presence would turn out to have been a countdown all along, a beautiful, terrifying time bomb hidden in the sky. Any world that wandered too near a star like this would not last long. Rock, metal, ocean, and air would be torn apart, heated, and scattered, its atoms flung into space to drift in the dark. In time, those atoms would cool and settle into new clouds, becoming part of other stars and other planets. Even the briefest, most fragile life that might arise near a supergiant would grow under a sky of doom, knowing if it could know that its days were as short as a spark beside something too large to feel real. Seen from far away, a red supergiant can look almost gentle, like a dim ember in a vast furnace. Up close, it is something else entirely. The danger is not only its size, but the storm of radiation pouring out of it. These are not sleepy giants. They are wild reactors hanging in space, their light and particles sweeping through everything nearby. The trouble begins with ultraviolet light. Our own sun sends out ultraviolet rays, but Earth is cocooned by an atmosphere and an ozone layer that soften most of the harm. Near a star like the behemoth, the flood of ultraviolet radiation would be so intense that any ordinary atmosphere would be stripped and shredded. Molecules would break apart, protective layers would be peeled away faster than they could form. A planet at Earth's distance with no extra shielding would see its surface sterilized almost instantly. As such a star ages and its core grows more unstable, it begins to produce even higher energy light, X-rays and gamma rays. These do not simply damage cells, they tear into the very structure of DNA, making complex life nearly impossible at the surface. Whole ecosystems could be erased not over centuries, but in moments. Their air ionized, their chemistry reset. To stand against that would require a planetary magnetic field and atmosphere, many times stronger than Earth's, and even then the safety would be uncertain. On top of the light come the winds. Supergiants blow out steady streams of charged particles, far denser and faster than the solar wind we know. Over time, such winds grind away at atmospheres, molecule by molecule, letting other space weather cosmic rays, plasma storms, bursts from flares reach the ground. Around the behemoth star, this maelstrom is shaped and reflected by its own dust. The torus of gas and grains that surrounds it acts like a strange mirror, absorbing some radiation but scattering other parts into new directions. Instead of a simple shield, it creates pockets and beams. Some regions strangely dim, others unexpectedly harsh. The star itself is not calm. It pulses and flares, its surface rising and falling, its brightness shifting as its interior struggles to hold balance. A single outburst can briefly increase its radiation by hundreds or thousands of times. A world that had slowly adapted to a deadly but steady background could be overwhelmed by one such tantrum. All of this unfolds in a galaxy whose chemistry is a little different from our own. The behemoth star lives in the large Magellanic Cloud, where the mix of elements, the dust content, and even the way gas cools and clumps do not perfectly match our local neighborhood. That means our familiar models of how radiation behaves and how winds flow need to be adjusted. There are more unknowns, more room for unpleasant surprises. In a universe where life usually grows in narrow, stable niches, red supergiants are the opposite, engines of change, radiating disruption simply by existing. Even if you could somehow hide from the light and wind, there is still gravity to contend with. Any planet moving around a star feels not just a simple pull, but a stretch. On Earth, we see a mild version of this with the tides. The side of the planet facing the moon feels a slightly stronger tug than the far side. So the oceans bulge, and water rises and falls on the shores. Near a supergiant, that gentle effect is magnified into something far more violent. A close orbiting world would be gripped by tidal forces strong enough to flex its entire crust. Its rocks would creak and shift, its mantles stirred like thick liquid. Super earthquakes and endless volcanic eruptions could become the norm, as the planet is kneaded by the star's changing pull. We see a small example in Jupiter's moon Io, where tidal heating keeps its interior molten and drives constant eruptions. A supergiant could do that to a much larger world, reshaping continents again and again. There is also a boundary called the Roche limit, the distance inside which a smaller body cannot hold itself together against the tides of a larger one. Cross that invisible line, and a planet can literally be pulled apart, its materials stretched into arcs and rings that circle the star like ribbons of dust and stone. Even beyond that limit, orbits would not be safe for long, because the behemoth star is losing so much mass over time. Its gravitational pull is slowly changing. As it lightens, planetary paths can shift, stretching into long ovals or drifting outward. Temperatures on those worlds would swing wildly as their distance from the star changed, making any long-term habitability even less likely. If there were multiple planets or moons, their mutual tugs could set up gravitational resonances around a calm star. These can lock orbits into stable rhythms. Around an unstable giant, they could become chaotic, flinging worlds inward to be consumed, or outward into the dark. And if, in its final stages, the star collects a thick accretion disk of gas and dust around its collapsing core, anything that wanders into that disk would be bathed in heat and radiation before spiraling to destruction. All of this paints a picture that is almost painfully clear. To orbit a star like the Behemoth is to live in a trap, too close, and you are torn, boiled, or blasted away. Farther out, your orbit shifts under your feet. Seasons lurch across extremes, and the clock of the star's short life is always ticking. Yet it is hard not to imagine what it would feel like to watch such a giant die from a safer distance. Picture a world sitting far out at the edge of a system shaped by the Behemoth star. From there, the giant fills a large part of the sky, a swollen red globe, surface mottled and restless. For generations, its slow pulsations, its occasional flares, have been part of the background, something your ancestors told stories about. Then the rhythm changes. The star begins to dim and brighten in less predictable ways. Spectral lines shift, if you have the tools to measure them, whispering that its interior is rearranging. You see great plumes of gas and dust lifting from its surface, visible even over days as hazy arcs. The calm red disk becomes speckled with brighter scars, flares and loops of magnetized plasma big enough to hide worlds. One day, the change comes all at once. In the heart of the star, the last fusion reactions run their course. The core collapses inward faster than anything you can easily picture. For an instant, almost nothing seems to happen. The light you see still comes from layers far above. Then the shockwave born at the center slams into those layers, and the star erupts. For weeks, the dying Behemoth outshines its entire galaxy. On your world, even if you are many dozens of light years away, shadows become razor sharp at night. The sky glows with a strange second day. If you are closer, the first flash of gamma rays and hard radiation might overwhelm your planet's protections, stripping air, damaging life, breaking circuits. If you are much farther, you merely watch, your instruments recording the rise and fall of brightness, the changing lines in the spectrum, the steadily expanding cloud of debris hidden inside that light. Ripples in space-time itself move outward as gravitational waves. You might detect them as tiny, passing strains in the fabric of distance, a whisper of the core's collapse. In time, the blinding brilliance softens into a glowing remnant, a nebula built from everything the star once was, and at its center, perhaps a neutron star or a newly formed black hole. The same ideas can be turned around in one more, quieter thought experiment. Imagine not a world that circles the Behemoth star, but one that lives behind it. The giant's thick torus of dust spans roughly a light year across, a ring of gas and grains that both blocks and scatters its light. Somewhere beyond that ring, tucked into its shadow, another system might exist, orbiting a smaller, gentler star. From that vantage point, the Behemoth would never be seen directly. Its face would remain hidden behind the curtain. Instead, your sky would be filled with a permanent, dim glow, a deep red twilight caused by light leaking through and around the dust. Day and night would blur. You would live in a world lit partly by your own star and partly by the diffuse shine of the giant's shrouded presence. Temperatures could be surprisingly mild, because much of the Behemoth's heat is absorbed before it reaches you. But the knowledge of what lies beyond the dust would seep into culture and story. On the horizon, or stretching across a great arc of the sky, the ring itself might be visible as a faint band, dust clouds lit from within, slowly shifting over centuries. Auroras at your poles could be fed not only by your own star's wind, but by streams of charged particles that have wandered from the Behemoth's storms. Meteor showers might be more common, as bits of the giant's discarded shell drift inward and fall through your atmosphere in brief streaks. If your people learned to build telescopes, their first deep instruments would likely be tuned to infrared, the very wavelengths best at piercing dust. You would become experts at reading what others can only glimpse, the subtle dimming and brightening of a buried star, the way its light is filtered by its own envelope. You might notice when the pulses tighten, when the spectrum shifts, when the dust flares unexpectedly. Long before the star's final collapse, you would know that your giant neighbor is nearing its end. When that end comes, even the shadow would not be safe from change. The dust torus that once softened the giant's presence would flare as the supernova's shockwave races through it, turning your twilight band into a brief, searing arc. For a while, the sky would be filled with too much light instead of too little. Instruments would saturate, myths would be rewritten. The gentle red veil that raised your civilization would be torn and lit from within. Living in such a place would never be peaceful in the way we imagine a calm night on Earth. Yet, it would shape everything. Your technology, your stories, your sense of time. You would be a culture grown in the long shadow of a single, impossible star, a family raised by a giant. In the end, the behemoth star will not simply fade. The fire in a star's heart is what holds it up. When that fire goes out, gravity finally gets to tell the last part of the story. And for a supergiant this huge, that ending is never quiet. Some stars slip gently into the dark. Others, like this one, choose a different path, ending in a single, overwhelming flash that can be seen across whole swaths of the universe. When a massive star runs out of fuel, the outward push from fusion suddenly weakens. There is nothing left to balance the inward pull. The core begins to collapse in on itself in a time so short it almost does not make sense to us. That collapse sends a shockwave racing outward, smashing through the star's layers and tearing them free. In that moment, the star releases more energy than our sun will emit in its entire 10 billion-year lifetime. For a giant with a radius around 1,500 times that of the sun, the scale of such an explosion is almost beyond imagination. If the behemoth star dies as an ordinary, if such a word can be used, Type 2 supernova, it will briefly outshine its entire host galaxy. For a few days or weeks, one star will rival the combined light of billions. The blast wave will plow through its dusty envelope and into the surrounding gas, shredding, compressing, and stirring as it goes. Some of those compressed clouds may later collapse into new stars, so that one death quietly seeds many births. But there is a more extreme possibility. Because the behemoth star is so luminous, so large, and has already lost so much mass in strange ways, it may be a candidate for something even fiercer, a hypernova. A hypernova is like a supernova, turned up by another factor of 100. An explosion so intense that it can be accompanied by slender, focused beams of gamma rays that reach across galaxies. The total energy released in less than a minute can match what the sun will emit over its entire life. For a moment, the universe listens. If the behemoth star spins fast enough, and if its magnetic fields are aligned just so, when the core collapses into a black hole, its final fury may be channeled into two narrow jets that punch their way out of the dying star. These are gamma ray bursts, the sharpest death beams we know. They are not simple explosions spreading evenly in all directions. They are more like cosmic spotlights, thin and intensely focused. In a few seconds, They can release more energy than a normal supernova does in its whole bright phase. We do not yet know for certain whether a red supergiant as bloated as the behemoth can produce a long gamma-ray burst. Most of the bursts we have studied seem to come from stars that have already shed their hydrogen envelopes, becoming compact objects called Wolf-Rayet stars. The behemoth star still wears its outer layers like a huge, loose coat, and those layers might smother any jet before it escapes. But some recent models hint that, with enough rotation and strong magnetic fields, even a giant like this might carve a beam through its own envelope. If such a beam ever pointed at a nearby world, it could strip away an atmosphere, break apart molecules, and destabilize an entire biosphere in moments. There are even ideas that, long ago, a gamma-ray burst in our galaxy may have played a part in one of Earth's mass extinctions. In that sense, these events are not only destructive, they may act as gardeners on a grand scale, pruning branches of life so that others can grow. We are safe from the behemoth star's direct aim. It lives in the Large Magellanic Cloud, more than 160,000 light-years away. Even if it sent a full-strength gamma-ray burst directly toward us, the beam would have spread and softened over that distance. It might still light our sky in strange ways, but it is unlikely to erase us from here. Such an event would be an opportunity rather than a threat. A once-in-a-civilization chance for telescopes to watch a titanic star die in exquisite detail. Whatever shape the final flash takes, something will be left behind. A star does not simply vanish, it signs its name in the remnant. For a giant like this, there are two main possibilities: a neutron star or a black hole. A neutron star is one of the strangest objects we can describe and still call matter. Imagine the mass of the sun squeezed into a sphere smaller than a city. In that state, atoms can no longer keep their familiar shape. Protons and electrons are crushed together into neutrons, and those neutrons are packed so tightly that a teaspoon of the stuff would weigh as much as a mountain. The pressure that holds such an object up against gravity is called neutron degeneracy pressure, a quantum effect that shows up when particles are forced into the same tiny volume. For the behemoth star to end this way, it would have to lose enough mass before and during the explosion that its core, after the blast, falls below a certain limit. If too much mass remains, even neutron degeneracy pressure cannot support it. Then the collapse continues, and a black hole forms. A black hole is an even more radical object, a region where gravity has become so strong that not even light can escape once it crosses a boundary called the event horizon. For an outside observer, whatever falls in simply disappears from view, leaving only its influence on the surrounding space and time. If the behemoth star retains a great deal of mass when it collapses, the black hole it leaves behind may be heavier than most stellar black holes we know. Depending on how much it sheds, it could end up as a relatively ordinary stellar mass black hole, or edge toward the mysterious intermediate mass range, where our observations are still thin and our theories still stretch. The precise outcome depends on a race between loss and collapse. The star is already peeling itself, flinging mass into its dust shell. If strong winds continue to strip it before the final moment, a neutron star might remain barely possible. If not, the core will cross the threshold from which there is no return. In a fraction of a second, it will shrink, release a flood of energy, and vanish behind its own gravity. From all of this, one quiet truth rises. The most important part of the behemoth star's story may not be its size or its brightness, but what it leaves floating in the dark when it is gone. Inside every massive star, there is a long, slow kind of alchemy at work. In the beginning, the core fuses hydrogen into helium. As the star ages and its center grows hotter and denser, helium fuses into carbon and oxygen. Later, in overlapping shells, the core passes through stages where neon, magnesium, and silicon are built. Each step releases energy, and each step is shorter than the one before, as if the star is hurrying toward its end. Then, in the last stages of a supernova or hypernova, something even more dramatic happens. In the brief chaos of collapse and rebound, shock waves and floods of particles push atomic nuclei together in ways that ordinary fusion cannot. In seconds, the rarest and heaviest elements are formed: gold, platinum, uranium, and many others. This is called nucleosynthesis, the making of new elements. And it is one of the main reasons stars like the Behemoth matter at all. When the explosion throws the star's outer layers into space, it is not tossing out empty gas. It is launching clouds rich with these newly minted elements, along with more familiar ones like carbon, oxygen, and iron. Those clouds expand over thousands and millions of years, glowing in X-rays, ultraviolet light, visible colors, and radio waves. We see them as supernova remnants, intricate filaments and knots in space that once were the living layers of a star. The Crab Nebula, Cassiopeia A, and many others show us this aftermath, each color in their light telling us about a different element drifting outward. Over time, those remnants cool and slow. Gravity, never in a hurry, collects them here and there into denser patches. Some of those patches eventually collapse to form new stars. Around those new stars, disks of dust and gas spin and flatten, grains stick together, and planets begin to grow. Our own sun is not a first-generation star. It was born in a cloud already enriched by earlier explosions. The iron in your blood, the calcium in your teeth, the oxygen in the air you breathe. These all began as ash from stars that died long before Earth existed. The Behemoth star will join that lineage. When it finally ends, its atoms will scatter through the large Magellanic Cloud, mixing with other clouds, slipping into the deep currents of galactic gas. They may someday be drawn into entirely new systems, perhaps in places where no one will ever know their origin. A bit of its carbon could end up in the bark of a tree under an alien sky. A few of its iron atoms might become part of the core of a rocky world that will never see us. Some of its oxygen could flow in the seas of beings who look up and wonder about their own stars. In that sense, the death of the Behemoth star is not only a catastrophe, it is a gift the universe gives to itself. The giant will burn, fall, and vanish. And yet, quietly, it will have helped write the next chapter of matter. New stars, new worlds, and perhaps, somewhere very far away and very long from now, new minds falling asleep under unfamiliar constellations, never knowing that part of what they are once belonged to a red supergiant that lived and died in a small, wild galaxy near our own. To understand the terrifying power of the biggest stars is also to understand something quiet and intimate about ourselves. We are not apart from them, watching safely from the sidelines. We are made from their ashes. Their stories run through our veins. When a giant like the Behemoth star finally dies, it does not simply wink out. It tears itself open. Its outer layers are hurled into space at tens of thousands of kilometers per second. A storm of charged gas and dust inflating into a vast bubble that can grow to span hundreds of light years. In the middle, there may be a tiny, collapsed remnant, a neutron star, or a black hole. But our eyes are drawn to the shroud around it, the glowing cloud painted in filaments and knots. These are supernova remnants, the nebulae that look from far away, like the handwriting of gods. Each one is different. Some stretch in ragged arcs, like the Veil Nebula, torn lace lit in X-ray and ultraviolet light. Others are almost eerily round, expanding shells drifting outward in slow, deadly symmetry. The Crab Nebula, born from a star that exploded while humans were watching 1,000 years ago, still expands today. Its delicate threads of ionized gas swirling in a kaleidoscope of motion and color. These remnants are not only beautiful, they are also useful, like open books in the sky. By splitting their light into spectra, astronomers can read which elements were forged in the blast: iron and nickel, cobalt and oxygen, and many others. By mapping their shapes, they can see where the original star was lopsided or where the explosion was stronger in one direction than another. The energy carried by the shock waves stirs and compresses nearby gas clouds, sometimes tearing them apart, sometimes nudging them into collapse and helping new stars to form. In that way, the death of one giant leads directly to the birth of many smaller suns, and the circle of stellar life quietly continues. One day, the behemoth star will write its own nebula into the sky of the Large Magellanic Cloud. Because that little companion galaxy is far enough away to be safe, yet close enough to be seen in detail, its supernova remnant would be a gift to every telescope we point at it. X-ray observatories could watch the hottest shocks. Optical and infrared eyes could trace the cooling filaments. Radio dishes could follow the expanding shell for tens of thousands of years. Each wavelength would tell a different part of the story of how an ultramassive star dies and how its dust and gas finally melt back into the space between stars, ready to become something new. We often treat death as an ending. In the universe, it is usually a handoff. Supernova remnants are the fingerprints of creation, scattered across the spiral arms of galaxies, gentle reminders that destruction and making new are, out there, the same act seen from different angles. The role of giant stars in all of this is larger than their small numbers might suggest. Most stars in a galaxy are modest, more like our sun or smaller. Truly, massive ones are rare, but they behave like loud neighbors in an otherwise quiet building. Everyone feels their presence. Even in their youth, as soon as they ignite, their hard radiation ionizes the gas around them, carving out glowing bubbles inside their birth clouds. Their winds sweep cavities in the surrounding material, shaping tunnels and shells and triggering fresh bursts of star formation along the edges. In their brief lives and violent deaths, these giants enrich their galaxies with heavy elements. The early universe was almost entirely hydrogen and helium, thin and simple. Only as generations of massive stars lived, burned, and exploded did the cosmic mix grow richer. Carbon for organic molecules, oxygen for water, silicon for rock, iron for cores and blood, gold and platinum for everything we call precious. All of these are the work of long-gone stars. Without them, galaxies would remain chemically poor, unable to build complex planets or the kinds of chemistry we associate with life. Their explosions also pump energy back into the galactic gas, heating and stirring the interstellar medium. Sometimes, this feedback breaks up cold clouds and slows the birth of new stars. Sometimes it compresses pockets of gas just enough to spark fresh clusters. In this way, massive stars act as both gardeners and storm systems, setting the pace at which galaxies grow, rest, and grow again. The behemoth star is already part of that quiet upheaval. Its enormous dust envelope carries material into the Large Magellanic Cloud, sprinkling heavy elements into the space between neighboring stars. When it finally explodes, its shock waves will ripple through its corner of that galaxy, lighting up the surrounding gas and sculpting its environment with one last act of luminous violence. If its core collapses into a black hole and later merges with another compact object, the event will send out gravitational waves, tiny ripples in space-time that observatories in distant galaxies might one day hear as a faint cosmic chord. The way we came to know this star at all is its own gentle story. At first, it was just a faint, red, slightly odd point in a crowded patch of sky. In the 1970s, a small group of astronomers cataloging infrared sources in the Large Magellanic Cloud noticed it, noted its properties, and moved on. Many red supergiants live in that galaxy. At a glance, this one did not seem uniquely special. The secret was in the wavelengths our eyes cannot see. As infrared astronomy matured, instruments on large telescopes began to peer through the dust that hides stars like this from ordinary sight. Observations from facilities such as the Very Large Telescope and the Spitzer Space Telescope revealed surprisingly strong infrared emission. That glow hinted that the star's light was being heavily reprocessed by a thick shell of dust, evidence of extreme mass loss. Piece by piece, using light from across the spectrum, astronomers built models of the star and its surroundings. They accounted for how dust absorbs and scatters different colors, how the star's own spectrum should look, and how bright it must truly be to produce what we see after all that filtering. High-resolution interferometry, a technique that combines the light from multiple telescopes to act like a much larger mirror, helped outline the dusty envelope itself. The numbers that emerged were startling. A radius far beyond most known red supergiants, a luminosity hundreds of thousands of times that of the Sun, and an envelope laden with several suns' worth of expelled material. Refining those values is still an ongoing project. Every improvement in infrared detectors, every new method of resolving fine details through dusty clouds, offers a chance to update the picture. Future instruments will likely sharpen the star's portrait again, tracing the flows of gas and dust in greater detail, perhaps even revealing whether a hidden companion star orbits within the cloak. Beneath all of the instruments and models, though, lies something simple and human. The behemoth star is, at its heart, a dot of light that someone once chose to look at more closely, to measure instead of ignore. From that quiet curiosity grew the realization that we are watching one of the largest known stars in the universe, living out its brief, impossible life in a nearby galaxy. One night, very far from now, or perhaps already in the past, it will end. Its light will flare, its core will fall, and its elements will join the great drifting sea from which future worlds will be made. And somewhere, someday, a being on one of those worlds may lift their eyes to their own night sky, feeling what you feel now in this gentle dark, that they too are made of something ancient and bright, forged in fires too big to see up close, yet somehow as close as their own heartbeat. Somewhere in all of this, there is not just a story about a star, but a story about us. A faint, dusty signal in a neighboring galaxy was noticed, measured, and patiently questioned until it turned into a cosmic legend. The behemoth star is not only a monster in the sky, it is proof of what happens when curiosity refuses to look away, when we keep asking what else might be hiding in the dark. To find a giant wrapped in its own ashes, radiating more than 280,000 times the light of the sun, and buried inside a cloak of dust, we needed more than a single telescope pointed at the sky. We needed many different ways of seeing. Early observations came from ground-based optical telescopes, which first picked up that something about this reddish star was odd. Its brightness shifted, its colors were strange. But through ordinary visible light, it looked faint and blurred, like a lantern seen through fog. Most of its glow was being swallowed and scattered by the donut-shaped shell of gas and dust around it. So astronomers changed how they looked. Infrared light, with its longer wavelengths, can slip through dust that blocks visible light. Observatories such as the Very Large Telescope in Chile began to paint a different picture. High-resolution infrared images showed that the behemoth star was surrounded by a huge, thick envelope. By carefully modeling that glow, scientists could estimate how much mass the star had already thrown off and how bright it must truly be inside the shroud. They realized they were dealing with one of the most extreme red supergiants ever found. Earth's air still blurs and blocks part of the infrared spectrum, so the next step was to leave the atmosphere behind. Space telescopes like Hubble and Spitzer joined the work. Spitzer, in particular, looked at the star in multiple infrared bands and helped reveal the size and temperature structure of its dust shell. From those clues, astronomers could refine the star's luminosity and radius, tracing its outline without ever seeing its surface directly. At the same time, spectroscopes quietly did their own magic. By spreading the star's light into a rainbow and examining the fine, dark, and bright lines etched across it, researchers could read which elements were present in the behemoth star's atmosphere and in the dust around it. Those spectral fingerprints spoke of heavy elements forged deep inside the star and carried outward by convective boiling and powerful winds. They also hinted at instability, at a structure already near its limits. To sharpen the blurred silhouette further, astronomers turned to interferometry, a technique that combines the light from several telescopes so that, together, they act like a single, much larger mirror. Instruments attached to the Very Large Telescope interferometer were able to resolve the shape of the dust shell and confirm its almost torus-like form. That, in turn, improved estimates of the star's actual size and the way it is shedding mass into space. Now, with the James Webb Space Telescope listening in the infrared with unprecedented sensitivity, and with future observatories such as the Extremely Large Telescope rising on distant mountaintops, we are beginning a new round of questions. Webb can peer deeper into the dusty cocoon, looking for subtle pulsations, temperature patterns, and perhaps even the faint signature of a hidden companion star. Each new instrument is like another sense added to our shared body, extending what our fragile eyes alone could never do. In that way, the behemoth star is as much a monument to our tools as to itself. Telescopes, spectroscopes, interferometers, space observatories, they are not just metal and glass. They are the shapes our curiosity has taken. Reaching outward, the faint whispers from this giant crossed 168,000 light-years of emptiness. We built the ears that could hear them. What those whispers say is unsettling and beautiful. By every tidy rule of stellar physics, a star this huge and fragile should live on a knife edge, or not at all. Yet there it is, swollen beyond the limits we once thought firm, wrapped in a dust torus built from its own lost layers, skirting the Hayashi limit where hydrostatic balance should fail. Its mass loss is so extreme that it seems to be dismantling itself in slow motion. Its size, brightness, and instability push our models right up against their boundaries and then lean a little further. Because of this, the behemoth star has become a kind of test for our understanding. The equations we use to follow a star's journey across the Hertzsprung-Russell diagram were not written with such extremes in mind. If this star is not a rare curiosity, but a member of a broader, hidden population of ultra-swollen red supergiants, then parts of our theory may be missing important pieces. Perhaps binary interactions play a greater role than we thought, with unseen companions spinning up and reshaping their partners. Perhaps dust production in massive stars is more efficient than our simulations assume, meaning that giants like this contribute even more to the dusty richness of young galaxies than we have realized. Watching the behemoth star is, in a sense, like skipping ahead to the last chapter of a certain kind of stellar life. Our sun will never follow this path. It is too modest. But many more massive stars in our galactic neighborhood are on their way toward red supergiant stages of their own. By studying this distant giant, we get to see, in advance, what happens when mass, light, and gravity are pushed close to their limits. It forces us to refine the words we use: what counts as a star, what counts as an atmosphere, where we draw the line between a swollen photosphere and a surrounding cloud. And woven through all the numbers is something softer: perspective. 1,500 or so solar radii, a dust shell roughly a light year across, a brightness hundreds of thousands of times that of the Sunday. These figures are so large that they slide through the mind without settling. The sun, which feels enormous and central to us, would be reduced to a small, pale ember beside this thing. If you could stand on a safe, imagined world that orbited the behemoth star at a survivable distance, the sky would not hold a single sun. It would be filled with it, a red, glowing curtain from horizon to horizon. And yet, here we are, on a small planet, around a very ordinary star, making tea, sending messages, worrying about tomorrow. All of this unfolds while, far away, a giant in another galaxy slowly unravels. Its light, softened by dust and distance, has crossed the dark for more than 160,000 years to reach us, carrying news of a life already well underway, perhaps already over. Even the behemoth star is temporary. Its furious brightness is a brief flare on cosmic timescales. One day, its core will give in, its outer layers will be thrown off, and its light will fade. What remains will be either a compact remnant or a quiet, invisible hole in space-time, wrapped in a nebula of its own ashes. From those ashes, new stars and worlds will grow. Maybe, somewhere, beings will look up at their own sky, never knowing that a few of the atoms in their bodies were once part of a giant that burned long ago in a small galaxy near ours. That is the quiet comfort hidden inside the terror of these enormous stars. They dwarf us. They could erase us if we were too near. And yet we are made of their gifts: the carbon in your breath, the iron in your blood, the calcium in your bones. All of it was forged in stars, not so different in spirit from this one. Giants die, but their matter does not vanish. It drifts, gathers, and becomes the raw material for new stories. As we listen to the behemoth star and others like it, we are not only learning about distant physics, we are listening to the older chapters of our own origin. We are small, yes, but we are also, quite literally, pieces of these ancient fires that have cooled into thought.